Professor Paul Hünermund, who is probably also someone you all know, big voice in causal inference, professor at School of Management and affiliated with Copenhagen Business School. And his research is well published in top research papers. I often reshare these papers. And in particular, he is also hosting at least in the past, the Causal Data Science meeting, which is this huge and very and great event on data science. So you can also look for this event that will take place next semester if you want to keep learning about causal inference. So now, well, the floor is yours.
So Martin did a great job at introducing this topic. He also emphasized a couple of times that causal discovery is really a hard problem, okay? Much harder than any of your standard predictive analytics tasks. And there's a lot of discussion in the causal discovery community about how accurate it really is in these like complicated real world settings. So benchmarks are really hard to come by. So what we're doing in this paper, and this is joint work with Jermaine Kaminski from Maastricht University and Yannick Bammens from University of Hasselt in Belgium, is to take a step back and ask the question like, okay, maybe it's too big of a goal to get the full DAG, right, with no uncertainties. And then we know actually that that's impossible in theory. But maybe causal discovery can still be a useful tool actually for exploration. Exploring new hypotheses that we can then go out and either test with A/B tests, with the typical A/B testing toolbox, or in some settings, right, if manipulation isn't possible, to use maybe quasi experiments or some other kind of quantification method. So that's the very simple method, but that I try, or very simple message that I try to pitch in this talk. Okay, so yeah, I mean, I don't need to preach to the choir, right? A/B tests are important area, field experiments to guide innovation and strategy. I mean, Ron has written a great book about this. But although in this community, we're very much focused on how to get an unbiased and very precise treatment effect, right? Actually, in practice, this might not be the most challenging problem. In practice, it might be to decide what to test next, especially in those kind of contexts where A/B tests are kind of cheap, right? So you have this huge hypothesis space, like the possibilities are endless, right? Should you go for the blue button with round shades, or like square ones but a slightly different shade of blue or whatever, right? Like these needle in a haystack problems, and so deciding that can be really tricky. Well, so our standard tools, right, exploratory data analysis or some kind of like exploratory regression analysis, of course, fully prediction based, right? And correlation isn't causation. Is that really a good guide for hypothesis generation? We say probably not. Probably we should apply a tool that takes the causality seriously, right? As an input for then later hypothesis generation and A/B testing. And there we're at causal discovery, right? Because that's a tool that starts from the data first, tries to get something causal out of the data. That's not always perfect, but maybe that can be useful. Well, first step for follow-up experimentation. So the core idea is really use the data to explore plausible causal structures, right? These candidate causal structures, and then use experiments if you can to confirm and quantify them. And causal discovery here is really a guide for this follow-up experimentation. So where does this fit, right? Judea Pearl's causal hierarchy that he describes in the Book of Why. We have this associational level, which is the predictive analytics and things like risk scoring, right? It's purely about the joint distribution of variables, right? Also statistical associations. Then we go to the causal layers, the interventional and the counterfactual. Causal discovery mainly sits at the second rung, the interventional level, the PY do X. And we know from theory, I mean, it's proven logically that there's this no causes in, no causes out principle. You always need some kind of expert domain knowledge as an input for doing causal learning, even if you can do a full randomization, right? The transportability problem will still be lurking. But like causal discovery can be a useful tool to focus experiment on high leverage edges, right there where's the biggest impact to be expected, detect possible confounding pathways, and also to make this conversation with domain experts about how to integrate domain knowledge. Causal discovery can also help there. This also relates, believe it or not, to an interesting discussion that is currently being held at the business school in the field of strategic management. So sort of these fields are converging, and at the causal data science meeting this year, we will have Teppo Ferlin from Utah, University of Utah, speaking on exactly this, the connection between strategic management and causal inference. So I'm really looking forward to that. Basically, in a nutshell, it's this idea that firms and managers, strategists, entrepreneurs all face this epistemological problem, right? Of what to test next, like what kind of strategy to apply next, what kind of business model to try out next, right? And often you cannot really experiment at scale, right? Like you have maybe 1, 2, 3 shots as an entrepreneur, as an aspiring one. You cannot pivot 5 times until you finally make it, although there's some of those stories in the business school as well, of course. So it's really about finding the right thing to test out, right? Having maybe an intuition and a guide. And that's also how we distinguish good managers, because good managers have this theory of value in their mind, right? And can generate like real high value hypothesis rather quickly and reliably. And here we think that causal discovery could be a useful tool, right? Yes, it's about expert domain knowledge. You need to understand your markets well. You need to understand your business well. But causal discovery can help as sort of an evidence-based exploration tool. Importantly, we're not saying that this is replacing any theory or experiments, right? It just helps to allocate basically resources, attention, and experimental budgets. So I'm really thankful for Martin giving this introduction, so I can skip over those things over here, the causal Markov condition and causal faithfulness. Right, in practice, we can never fully learn the complete DAG. It will always be an equivalence class of DAGs that has certain edges undirected, but those we could actually later then test with follow experimentation. This is one of my favorite examples that I use in class to introduce the so-called PC algorithm, which is one of those foundational algorithms in causal discovery, right? Like if we had a ground truth model like this is the famous absorptive capacity model from Cohen and Leventhal, gets taught in technology and innovation management classes all across the world. Basically, very simple model saying that firms are doing research and development not only to increase their technical knowledge directly, right, which is this directed edge from here to here, but also to increase their absorptive capacity, which is basically the possibility to learn from what's happening in their industry. Right. So in their industry, there's currently an AI boom going on, but you need people in the organization that can digest this scientific knowledge. That's also presumably why many people are here at the Causal Summit today. And that's you increase this absorptive capacity by increasing your own R&D spending. Sorry for flipping. Here we are. Okay. Such a ground truth DAG would actually imply 2 independence relationships. Okay, so based on this deseparation criterion that Martin was explaining. So here, if that's the ground truth causal model, we would expect R&D expenditures and industry spillovers to be independent, as well as absorptive capacity and industry spillovers to be independent. And causal discovery now flips this on its head, is saying, okay, what if we only had those independence relationships, and those we can test in the data, right? Not always like to 100% accuracy, but independence testing and conditional independence testing is a known problem, and we can apply various tools. How far will we get in recovering this ground truth DAG? Right? And this is really, in a nutshell, how the PC algorithm would go about, right? You start with a complete undirected graph, which is basically no knowledge, right? So all the variables are connected. There's no causal information here, because the causal information is actually about the absence of edges. That's the real causal knowledge, that some variables don't affect each other causally. Then the second step of this PC algorithm is to learn the so-called skeleton graph, where you have edges, but they're undirected. And here you can rule out edges based on these independence relationships down here. If two variables are independent, there can be no direct edge between them. So you see here the edge between R&D expenditures and spillovers, and absorptive capacity and spillovers to be removed. And then in the third step, you're trying to orient those edges. There's where the causal direction comes in, okay? And here you can do that in the following way. You can infer that it must be absorptive capacity causing knowledge and spillovers causing knowledge. That is based on this collider structure that Martin was explaining. So that you infer from this collider structure. Okay, and here this works in this example. You can orient 3 out of 4 edges. The last edge between R&D expenditures and absorptive capacity, the algorithm is not able to recover. So here there remains epistemic uncertainty. Okay, and that's the so-called equivalence class. Both of these DAGs, one where R&D expenditures is causing absorptive capacity and the one where it's the other way around, are both equally compatible with the data, right? So we have essentially 2 DAGs here that are compatible with the data. But compared to the ground truth, right, this was the ground truth, actually this looks not bad. Right, this looks pretty interesting and already pretty useful. So maybe the PC algorithm and various other variants that Martin was describing, right, FCI and hybrid algorithms, could be useful guides to direct attention for follow-up experimentation. Different methods, score-based and constraint-based. Martin and I will probably focus here on this constraint-based side, but these are the finer details for what I'm trying to tell you. Both of these approaches would work. Okay, so how do we envision that, right? So of course, you need to define the decision problem. You need to find target variables, KPIs that you're interested in. You need to select the variables to put into this causal discovery algorithm. And there was already a question in the Q&A on this. Here we urge people to rely on the domain knowledge, right, in the organization. Talk with experts, try to elicit the variables that really play a key role. Then run a causal discovery algorithm like this PC algorithm that I was explaining to you. And then based on the output of that PC algorithm, design follow-up experiments on those edges that give the highest expected value. And for that, you can also rely on quantification methods from the training data, basically. And of course, this we see as an iterative process, right? You can do that across several iterations. Okay, I want to show you this in a case study, okay, based on a real-world data set. Not that I think, or I'm jumping ahead, not that I think that this is the best data set to illustrate this, but we also wanted to avoid here like this typical cherry picking, right, where it's always like one context that fits 100%, but then if you apply it to a different context, it's not so great anymore. And also, this is a data set that is freely available, so you can replicate this analysis if you want. So it's about, a paper Moro et al. 2014 and about marketing and conversion rates in a bank, in a Portuguese bank. So basically customers being approached about loan offerings, right? And you're measuring whether those customers convert, whether they actually sign up for the offering. The good thing about the data set, it really spans a wide variety of contexts. So you have information about customer characteristics, whether they're married, whether they're currently unemployed, whether they have already a loan with the bank, right? You have context variables like the macroeconomic setting. You have information about the context strategy, and of course, the main KPI, whether the customer converted and bought into your offering. So then, other variables, of course, no data set is complete, right? You will always have missing variables. And of course, that's actually a key assumption in causal discovery, But we hope that by covering so many bases, that it at least still gives us a useful picture. Okay, so I'm skipping over a lot of the details, but how would that look like in practice? Okay, if you apply this kind of PC algorithm to this data set, and I'm happy to share the code with you if you're interested, you would come up with such a graph over here. Okay, and now, of course, we could look at this picture forever, right? Like one called it once a spaghetti graph when I put out these stacks with many variables. But one thing is already interesting. Okay, so you have 18 variables here in this context. It's a medium-sized problem, right? It's not 1,000 variables, big data, but it's also not just a regression with 4 variables like I showed you earlier. And if you have 18 variables, you have in principle, right, n times n minus 1 over 2 possible edges, right? In this case, 18 times 17 over 253 possible edges. The PC algorithm, depending on how you choose the significance level, which is here a pruning parameter, right, or like a nuisance parameter, gives much fewer edges than 153. Okay, so you can already rule out a lot of candidate hypotheses simply by this first step of causal discovery. Then what you see is actually 2 clusters that are completely unconnected. Okay, so the macroeconomic variables like the current price index and consumer confidence index here, they are related to other variables like the employment rate, right, or the variability of employment, and also whether the campaign was done during the summer months, but they're not related to the other variables here with any edges. So they can also not have a causal effect on our focal variable conversion. Okay. Also interesting insight. And then, yeah, many more possible interpretations here. So, for example, right, customer characteristics, whether customers that have a university degree seem to be more distantly connected, if at all, to conversion compared to, for example, things like, well, the contact method. Okay, so this is whether customers were approached via landline or via cell phone. And mind you, this was 2014, so more than 10 years ago. And also the duration of the call. Okay, and if you try to quantify this, you find this actually inverse U shape or more like decreasing marginal returns of duration. So longer duration increases conversion probability, but has decreasing returns, at least in the training data. Right, and these are actionable insights, right? For example, who to approach, whether you approach people with a certain, well, human capital level or married, or whether they already have a housing loan with you, right? This would be not so great ideas according to the causal discovery algorithm. At the same time, as management in this context, you can affect the duration, right? You can train your people to try to prolong the marketing calls and also the contact method, whether it's a cell phone or landline. Okay, I'm trying to wrap up. Okay, so how can this be useful? We think that this creates useful insights for hypothesis generation, right? You can rank these possible interventions by, well, manipulability. Okay, you as a bank, you can't affect the interest rate or consumer confidence index, but you can affect who you call, right? So this is related to how easy it is for you to manipulate those variables. I also interpreted for you this proximity to the KPI, right? Like some variables were less connected to our target variable conversion than others, and that would be something to rank those interventions on. Then you can try to do this quantification and try to see at least like what's the causal association if you want, right? Because we're always careful to say this is a true causal effect here. We want to elucidate that in follow-up experimentation, but in the training data, we can at least try to quantify this effect. And of course, cost play a role here too. Well, limitations and good practice. Again, right, the per causal hierarchy, no causes in, no causes out means also here there's no free lunch. Causal discovery relies on a lot of assumptions, Markov assumptions, faithfulness, causal sufficiency. And we do believe they will be violated one way or the other in practice, but we think, and there's good evidence from simulations as well, that still the signal is there in all of that noise, right? If you're really worried about hidden variables, there's some causal discovery algorithms that can deal with that. For example, this FCI algorithm, but still there are no magic bullet, right? If you weaken the assumptions, also what you will get out of the data is less. And yes, stability matters, right? So this was also something touched upon already. You can try to use standard resampling methods, stability selection, compare algorithms, right, in different sample splits. This would be all ways to look at how stable all of this is. And this will definitely not replace domain knowledge, right? But it can also be a guide, right, for talking with your stakeholders, right? Like try out the causal discovery and confront your stakeholders with it, and maybe together, human in a loop, you will find something really interesting. All right, I will skip over the last slide, and thank you for your attention.
Thank you very much, Paul. That was very interesting and perfect to continue after Martin's talk. We are a bit over time, so let me try to say first. I'll say one thing because many of you mentioned this, and I think one thing that's particularly fascinating with causal inference is that to do well causal inference, you always need two things: technical knowledge and domain knowledge. And if you lack one, it's not working. And domain knowledge is really useful, sometimes exactly as you highlighted here, to disentangle or answer some questions or disentangle some problems. Maybe because we are a bit over time and we need to maybe quickly take a break. Just a very short question, because I'm not sure you mentioned this. Within these models, do you have an evaluation of the certainty and uncertainty of the answer?
No, this is exploration, right? So this is a bit outside of the testing logic. Yeah, I think there are approaches in causal discovery trying to I think I remember a conference 2 years back where someone derived confidence intervals for causal discovery, and it was sort of the star paper of the conference because no one has done that before. Of course, that relies on assumptions, right? Like actually one good thing about DAGs and causal discovery, right? These edges are fully non-parametric. Right, like they can take any shape, form, functional form, but that also means that it's very hard to quantify in a traditional sense, right? Like uncertainty about those edges. But maybe Martin has some more insights on that. But it's generally a tough problem. Here we're thinking about exploration, where I think confidence intervals would not be what you want to have.